Hey guys, here's the review for Spiral 12. We're going to start out with some trig equations, and at first we're going to look at 2 cosine squared minus 3 cosine x equals -1. To me, I see that we've got some squared and some non-squared. This is going to be something I have to factor in a quadratic sense. So I'm going to bring everything over to one side, and I'm going to write that as 2 cosine squared x minus 3 cosine x plus 1 is equal to 0. And in factoring this is going to factor into 2 cosine x minus 1 and cosine x minus 1, which means we get 2 cosine x minus 1 equals 0, where cosine x is equal to 1/2. That's true at pi over 3 and at 5 pi over 3. We also get cosine of x minus 1 is equal to 0, which means that cosine of x is equal to 1. That's going to be true at 0 and at 2 pi. Based on my interval, I can use both endpoints, so all 4 of those answers are correct. For my second one, 3 tangent squared minus 9 is equal to 0. Since I don't have a non-squared term, I might just try to do this with square roots. Let's add 9 to both sides. So plus 9, and we get 3 tangent squared x is equal to 9, divide by 3. Tangent squared x is equal to the square root of 3. Square root both sides. I get tangent of x is equal to, somehow I jumped the gun here with the square rooting. So this would be equal to 3, not the square root of 3. So tangent of x should be equal to the square root of 3, or tangent of x is equal to the square root of, or the negative square root of 3. To me, this just means that this is going to fit all 4 angles of one family. Now I've got to figure out what family of angles we're talking about. With tangent, I always have to figure that out by hand. I know tangent is opposite over adjacent, and I need to set up a triangle in such a way that I get square root of 3 as that ratio. I know square roots of 3 come from 30, 60, 90s, so maybe make this 60. And that would be root 3 over 2, 1/2, and 1. So tangent of the 60-degree family, so that's pi over 3, is equal to root 3 over 2 over 1/2, which when I divide, I get the square root of 3. So that's actually the angle I'm looking for. That means that x equals pi over 3, x equals 2 pi over 3, x equals 4 pi over 3, and x equals 5 pi over 3. I've got to use all 4 because I have the plus and the minus version of this. Finally, we're looking at 4 sine x plus 7 over 3 is equal to 5 over 3. First thing I might do is get rid of that 3 in the bottom by multiplying both sides by 3. Cancel, cancel. Oh, and that cancels too. That leaves me with 4 sine x plus 7 is equal to 5. Okay, maybe minus 7 from both sides. And I get 4 sine x is equal to -2. Divide both sides by 4, and I get sine x is equal to -1/2, because 2 over 4 is the same as 1/2. Sine x is equal to -1/2. Those are going to be my pi over 6 family, and those are going to be on the left side. So we're looking at x is equal to 5 pi over 6, and x is equal to 7 pi over 6. Here we're looking at some identities. First thing I might do is to take a look at my first identity and try to convert everything to sine and cosine. So that's sine x. Then I've got sine x over cosine x, and cosine x can stay the same. I might write that as cosine over 1 because I have some fractions in there. Cotangent of x is going to be cosine x over sine x. Multiply that by cosine of x over 1. And I also might write this guy over 1. Okay. First thing I notice is that I can clean up the inside a little bit. And my cosines cancel out in my first term. Nothing cancels out in the second term. But I could write this as sine x over 1. Again, I'm not going to distribute quite yet. Here we're going to have sine x over 1 minus cosine squared x over 1. Okay? Now, sorry, that should be over sine x. Whew. Now I'm going to distribute this through, and sine x times sine x is going to be sine squared x. Sine x times cosine squared x is going to be sine x cosine squared x over sine x. Those cancel out. I'm left with sine squared x minus cosine squared x. Okay, but here's the thing. I want everything in terms of cosine squared x. So what I might do is realize that sine squared of x is the same as 1 minus cosine squared x. And rewrite this as 1 minus cosine squared x minus cosine squared x, which comes out to 1 minus 2 cosine squared x, which is equal to 1 minus 2 cosine squared x. And that happens to work. For my next one, I've got to convert secant and cosecant to tangent. I know those are both related to some Pythagorean identities. In fact, I could use these lovelies right here to take a look at them. So that means that secant squared, I could write that as tangent squared x plus 1, that's my secant part, minus 1. And then the bottom for cosecant squared, I could write that as 1 minus, and that's going to be 1 plus cotangent squared x. Okay, I'm going to clean that up a little bit. Plus 1 minus 1 cancel out. 1 minus 1 cancel out. I'm left with tangent squared x over negative cotangent squared x. The fastest way for us to work with this would be to rewrite this as tangent squared x over, and cotangent is the same as 1 over tangent. So that'd be negative 1 over tangent squared x, which is the same thing as tangent squared x multiplied by the reciprocal of the bottom, which is tangent squared x over negative 1. Tangent squared times tangent squared is tangent to the 4th. And the fact that I'm dividing by negative 1 means I can put that negative out front. You could also have converted this to sine and cosine at this point, or at the beginning if you wanted to, and that would get you to the same place through a different way. Now I'm looking at some sum and difference and double angle identities. This first problem is going to be way harder than anything that I would give you on a spiral. I'm not going to give you a proof, but I thought this was kind of a cool problem and gets at really understanding how to use plugging things in. So if sine of x plus y, that means my x is a and my y is b, times sine of x minus y, I'm going to use this formula twice. One's for plus, one's for minus. My goal is to make sine squared x minus sine squared y. So let's begin by plugging in the first one. We do this part in red. So we get sine of x cosine of y plus cosine of x sine of y. And we do the second part in blue, and we get sine of x cosine of y minus cosine of x sine of y. Okay, now we've got to do some distribution. I'm going to multiply. We get sine squared x cosine squared y. I'm going to distribute that again. We get minus sine x cosine y cosine x sine y. That's a handful. I'm going to do some more distribution. I'm going to change colors. We're going to have plus cosine x sine y times sine x cosine y. And then finally, that's going to be minus cosine squared x sine squared y. Oof. Okay. What I'd like for you to notice is that in looking at these two terms, they happen to be the same exact thing, but opposites. what that means to me is that those are going to cancel out, and that's going to leave me with sine squared x cosine squared y, and then minus cosine squared x sine squared y. Okay, that gets me almost to the end here. Since I want everything in terms of sine, I might try to convert these guys to sine using my Pythagorean identity. That'd be writing this as sine squared x times 1 minus sine squared y. And we've got minus 1 minus sine squared x times sine squared y. And let's see what happens when we do some distribution. We get sine squared x minus sine squared x sine squared y. Okay. For my second part, I'm going to have minus sine squared y, and then minus minus is plus sine squared x sine squared y. And what I'd like for you to notice is we have a negative and a positive version of that. Those are going to cancel out, leaving me with sine squared x minus sine squared y. That's a hard proof. That's requires a lot of algebra, but I think it's a pretty cool problem as far as seeing how things can cancel out and simplify. Okay, for number 4, I'm trying to find an exact value for this, which means I've got to convert it back to one of those formulas. Okay, cosine cosine plus sine sine. That means I'm using this guy, and I'm using the bottom version, which is going to be cosine of a minus b. So this is the same thing as cosine of a minus b, where a is 10 and b is 55. In other words, we're looking at cosine of 10 minus 55, cosine of negative 45 degrees, which is the positive square root 2 over 2. Finally, we're looking at exponential graphs. You're going to have a couple sketching things on the review and a couple writing equations things on the review. When you're asked to sketch a graph of the following, there are a couple things I need you to put on the graph. The first is you need to include 3 points. You should include the y-intercept because that's a nice easy point to find. Or in this case, it's going to be a y-intercept-like point. And you need to include your asymptote. That's how I'm going to look for points as far as grading this thing. I also really should have given you a grid, because these things are awful to grade if you don't have something that's a grid for you to look at. Okay. There are a couple ways for us to do this. The easiest is for us to think about this in terms of a table, and that's probably the best way for us to handle this graph. Another way would be to graph 3 to the x, and then graph that in terms of transformations. That is a great way to think about this. That's a more mathematical way to think about this. But as far as what you're being asked to do here, a table is probably your best approach. The one thing I will get out of this initially is realizing that my asymptote's at 0. So I'm going to draw my asymptote in first, label that y equals 0, and then I'm going to put some points in. Okay? I notice that I've got x minus 1 up there. A great point to choose to start off would be a number that makes that 0. So if I do 2 times 3 to the 0, I get 2 as an answer. So let's go 1 comma 2. I can then go maybe 1 up and 1 down from that. I think that's probably a good choice. By the way, this would have been your x-intercept before the translation. The y-intercept. So that's why I was talking about a y-intercept-like point. So looking at the next point, maybe looking at 2. So 2 times 3 to the 1, which would be 6. So 2, 1, 2, 3, 4. That's going to be 2 comma 6. And then I need to see 1 point maybe on the other side, so maybe 0. And if I plug that in, I get 2 times 3 to the negative 1 is going to be 2/3. So we're looking somewhere like here. My graph would look like this. I've identified 3 points, clearly marked, and an asymptote. And I've sketched a curve along that. This is going to be worth 5 points. You're going to get 1 point for each of those points, 1 point for the asymptote, and 1 point for a curve that looks like it's the right shape. If, for example, you were to do this on your calculator and only have the curve in approximately the right place, you get 1 out of 5 points. I'm going to skip to number 7 because that's doing the same process, and I think it's useful to talk about that twice in a row. So the first thing, again, I'm going to do is look at my asymptote. That's going to be at negative 3. So 1, 2, 3. Y equals negative 3 is going to be my asymptote. I've got to draw that first. That's one of my 5 points that I need to get credit. And again, then I might do this as a table. I like choosing a number that makes the top equal to 0. So that's going to be negative 1. And we get 1/2 to the 0, which is 1, minus 3 is negative 2. So negative 1, negative 2 is going to be a point. Okay, and I labeled that. Next point, I might go 1 up from that, and I might go 1 down from that. So if I do the first one, 0, that's going to be 1/2. 0 plus 1 is 1. Minus 3 is going to be negative 2.5. So we're at 0, comma, negative 2.5, or negative 5 over 2. I know I harp on fractions, but decimals are easier to write sometimes. And then I might do the third point would be negative 2. And in looking at that, so that's 1/2. Negative 2 plus 1 is negative 1. So that's going to be the reciprocal 2 minus 3 is negative 1. All right. So negative 2, negative 1. And you draw an exponential through these points. It would look something like this. And again, you get 1 point each for the 3 labeled points, 1 point for the asymptote, 1 point for the curve. You have to include those points. All right, given an exponential function, y equals ab to the x, that goes through a couple points. Key point here, I don't tell you explicitly to find y equals ab to the x, but you need to find that equation. I'm going to start with my 0, 2 point. So y is equal to ab to the x. I don't know why I just rewrote that. I'm going to plug in 0, 2. 2 is equal to a b to the 0, which means that a is equal to 2. I'm going to use that point now. So y is equal to 2b to the x. And plug in this point. So 27 over 4 is equal to 2b to the third. Okay, divide by 2. 27 over 8 is equal to b to the third. Going to cube root both sides. And this actually comes out to a perfect cube root because the cube root of 27 is 3. The cube root of 8 is 2. So 3 over 2 is equal to b. That gives me the equation y is equal to 2, 3 over 2 to the x. Okay, that's really the bulk of this problem. The one thing we have to do is actually answer the question, which is to find the y value when x equals negative 1. So if we found our equation, what that means is I'm plugging negative 1 in for x. So y equals 2, 3 over 2 to the negative 1. In other words, y equals 2 times 2 over 3, which is 4/3. Second one of these, similar question. I regret that I didn't give you the explicit instruction. To find an equation y equals ab to the x that actually fits this, we go through the points 0, negative 3, and negative 1, 1. Let's take 0, -3 first, and we're going to use that to find a. So -3 is equal to, crap, this is not going to work. That's okay. We'll make that -1, -1, because we don't want to deal with that. So -3 is equal to ab to the 0. In other words, -3 is equal to a. So I've got an equation starting out, y is equal to -3, b to the x. The reason that we had to do this way was because you can't get a negative value here and then a positive y value without moving this up or down. So we had to make that negative as well. So that makes that -1 is equal to -3, b to the -1. So I can write that as 1/3 is equal to b to the -1. In other words, b is equal to 3. Okay, that gives me an equation. Y is equal to -3, which is my a, times 3, and that's to the x. All right, I've got to finally plug in my last point. Y is equal to -3, 3 squared, and that's going to come out to -27. For this particular one, you probably could have figured that out by using some other methods, and that would be okay. I'd really like you to get used to getting that equation first, though.